due to the fact that pi bonds don't rotate. If I have 2-butene or butene, there's actually two isomers, the cis and the trans. And the cis, the two ends are on the same side. Or we might say the double bond has both groups on the same side, where the trans, you can see it has a different shape, where the rest of the chain is on the opposite sides. So we call that trans, and the other one's cis. Now we could have a molecule that has sigma bonds everywhere, but if it's a ring, then that locks some of the bonds from rotating. This bond here can't rotate, so it locks these groups into position. So if I was going to name this, first we figure out that this is a 5-membered ring, so we get the cyclopentane figured out. Then we start numbering at 1, or over there at 1. It's kind of symmetric, doesn't really matter. So we have 1,2-dimethylcyclopentane, but that could be easily confused with this thing here. So since the two groups are on the same face of the ring, think about heads and tails, this is on the same side. You think of this as a coin. So we named this cis, 1,2-dimethylcyclopentane. And here the two methyl groups are on opposite sides. It's still named 1,2-dimethylcyclopentane, but we put the word trans, and that tells you one methyl is on one face of the ring and the other is on the other face of the ring. So we call these geometric isomers, and we'll have more to say about these later. How stable are cyclohexanes? That was a Freudian slip. How stable are cycloalkanes? 5- and 6-membered rings are the most common, found in nature. Carbons of cycloalkanes are got to be sp3 hybridized. And there's that magic angle of the perfect tetrahedron, 109.5. Well, we can probably make a cycloalkane that doesn't come close to that magic angle. When a cycloalkane carbon has an angle other than 109.5, there will not be optimum overlap of the orbitals, and the compound will have angle strain. The strain of the angle is sometimes called Baer strain. Then you take Baer aspirin. Actually, the guy who invented Baer aspirin probably came up with this concept. So that's some guy's name. In honor of Adolf von Baer, who first explained this phenomenon. Torsional strain arises when the bonds are eclipsed. So here's our magic angle, 109.5, and you can see the model kit does not like it. So these want to be 109.5, but they need to be 90, right? And you can see it's bending the plastic. And you can see if we look down two carbons in like a Newman projection, they're eclipsed. They're all eclipsed. It leads to bent bonds. And of course, the worst case would be cyclopropane. And it's about destroyed the model kit. Now it's bent those bonds. The ring strain of the planar cyclopropane results from two factors: angle strain from the compressing of the bond angles to 60 rather than the tetrahedral angle of 109.5, and the torsional strain where they're eclipsed. So if you look here, I've fixed my model just a little bit. This bends slightly. It relieves some of that. So now you can see it's not a flat plane. It's got a little bit of a fold in it. So cycloalkane with 4 carbons is going to adopt more non-planar conformation, leave some of the angle strain, and if I make this perfectly flat, you see it's eclipsed. Ooh, look there, I tweaked it a little bit, now they're not so eclipsed. So I put a fold right in the middle. And now they're trying to be a little bit staggered, not perfectly staggered. Might look kind of like that. And here you can see it. I hold it relatively flat. This part is popped up. It's like a flap on an envelope. And you can see it either goes off to that side or off to that side. What that does is it takes some of the eclipsed out of it. If I flatten it, then the Newman projections have everything eclipsed. But as soon as I put that little fold in it, takes that out. It takes it out everywhere. Well, except for the bottom of the envelope. So, the scientific word, puckered conformation, reduces the eclipsing of the adjacent methylene groups. I always think of flap on an envelope. And cyclohexane comes the closest to having a perfect 109.5 degree angle everywhere. And if you look at it, you might imagine this being the back of a chair, 2 armrests, and your feet hang down there. So this is called the chair conformation. This one here is a boat conformation. And in the boat, we can see we stagger the 2 sides, stern and bow of the boat. The rails of our canoe, they're eclipsed. So this is the boat. This is the chair. The chair has everything in the eclipsed conformation. Let's go back to the boat. So the stern and bow are eclipsed, but the rails of the boat, the rails of the boat are eclipsed. Bow and stern, they're staggered. And so there's this thing called a twisted boat. There, now I've twisted it, and that's put some stagger into the rails of the boat. So the chair conformation is the most stable conformation of cyclohexane. And here's the Newman projection. The chair has no eclipsing interactions, and all the bonds are the magic 109.5 degree bond angle. Here's the boat, and if we looked at the Newman projection, we kind of did with the model kit. I said the rails of the boat were in the eclipsed. We stuck our eye over here, they weren't eclipsed. This has this thing called steric hindrance here with these, what we might call flagpole hydrogens. And then you saw me make the twisted boat, which undid some of this eclipsed hydrogens. Eclipsing bonds result in torsional strain. Twisted boat conformation has fewer eclipsing bond interactions and less interference between the flagpole hydrogens. So here is lowest energy conformation is the chair, and here is where we go through this half chair, where this portion here is now all planar, and it flips up into the boat. Boat's right there. If I put a little twist in the boat, or if I twist it the opposite direction, there's the twisted boat, back up to the half chair, and back to the chair. 42 kilojoules between the chair and the half chair, 23 between the chair and the twisted boat, 29 between the chair and the boat. So in the chair position, we have, right now we just have hydrogens, but we can label these hydrogens as either being axial or equatorial. So the way I like to think about this is the North Pole up here, South Pole down here. What separates the 2 hemispheres of the planet? What's that line? It's geography class. Yeah, the equator comes from the word equatorial, or equatorial comes from the equator. Maybe. Don't quote me on that. But we see all these hydrogens in the equatorial, or on the equator, are pointing out, and all the other hydrogens are either pointing towards the south pole or the north pole. And the world spins on its axis, and basically the axis is defined as north pole to south pole, that line. That's where it spins on there. So now it's time for art class. One of the reasons why I like the textbook that we have, the reason why I adopted it was the substitution elimination reactions and what a good job it does explaining that. But it also explains how to draw a cyclohexane ring. And it might say make two parallel lines like that. Slanting parallel lines. And then you make two more parallel lines. And then you connect these. And that looks like a pretty good cyclohexane. I'm pretty proud of myself right at the moment. So I'm going to take and I'm going to think about all the axial hydrogens. And now I'm going to draw in all the equatorials. Oh, I missed an axial. I missed that one. Now these are the hardest. Like this one here, it's coming out kind of like that. And this one becomes difficult to draw in there too. And this might be important. Let's name this. Well, the easy part is cyclohexane. All right, let's label these 1, 2, 3, 4. All right, so how about a 1, 4? Oh, did I leave myself enough room? Methyl cyclohexane. You hand this on the quiz, you're getting -1/2. Do we want to name this cis or trans? Everybody is pretty sharp here. That is right. Trans. All right, well, we'll come back to drawing a cyclohexane. Now we can take our folding chair and make the footrest the backrest and the backrest the footrest. And when we do that, we see all the actual positions become equatorial, and all the previous equatorial become actual in the new conformation. And I used to have a real nice model for that. I'd make another one, but we might as well. Here's an actual methyl. If we flip the chair right, we can get it into an equatorial position. So here's a Newman projection, and we can see it's staggered. Everything's staggered. And now we flipped it, and now it's in an equatorial position. So here's an actual hydrogen, actual, axial, 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 and this is now an equatorial. There's the axial position, and the rest is all the ring. So when we have substituents in the axial position, they interact with the other axial items, other two hydrogens here. And so if we just call this 1, 2, 3, 1, 2, 3. So we call this a 1,3 diaxial interaction. So if we back way up to some space-filling model like this, you can really see here's that CH3 methyl group, and it's smashing these red hydrogens right here. This model here, you can't see that going on, but in nature doesn't like this so much. And so these bonds can rotate. The rotation of sigma bonds give rise to different conformations. Here is a conformation where the methyl group is in the axial position. Now it does not have the 1,3 diaxial interaction, and physical chemists have calculated this out or measured it somehow, and it's more stable by 7.1 kilojoules. And notice the equilibrium arrows. And maybe in Chem 2 you converted a delta G into an equilibrium constant. Axial substituent interferes with the actual hydrogens, and we call that a 1,3 diaxial interaction. So here's your Chem2 equation. An equilibrium constant is equal to E raised to negative the Gibbs free energy divided by RT. And so here is the energy difference. And if we put a T-butyl group for X, it really wants to be in this equatorial position. If you have all these 3 methyl groups around this. And so 23 kilojoules. It's going to make this arrow real big. All right, that's a good place to end.